Okay, so we're going to take a look at section 5.7 for the next little bit here. This section is going to basically be some different forms of integrations we can do. So first we'll write down a couple of equations. We're going to say we could write natural log of x as the integral from 1 up to x of dt over t. As long as the x is greater than 0. So we get this way of writing natural log if we wanted to. And then we're going to get a bunch of other things here. We get arcsine. We have a way of representing arcsine of x. We can represent this as 0 up to x of dx over square root of, sorry, I wrote dx, I meant dt, over, because since x is the upper limit, we got to change the variable to a different name. This would be square root of 1 minus t squared. And this would be for x's between -1 and 1. So we get these two equations we're going to use a little bit, and then most of the stuff for this section is going to come from the next bit where we deal with the derivatives of integrals of inverse trig functions. So we have the integral of dx over the square root of 1 minus x squared. That will equal arcsine of x plus c. We have the integral of dx over x squared plus 1. That will equal arctangent of x plus c. And then down here we'll have also the integral of 1 over absolute value of x, square root of x squared minus 1. That will equal, it's dx over all that. That will equal secant, inverse secant of x plus c. So we get these three equations, and we're going to be dealing with these for a bunch of the examples. All right, so first example. They say we got the integral from 0 up to 1 of dx over x squared plus 1. They want us to calculate what is that. So we kind of compare this and we say, hey, dx over x squared plus 1, that sure looks like this equation here. And so we can say, well, that is actually that equation exactly. So when we want to evaluate this, this will be arctangent of x evaluated at 0 up to 1, which will be arctangent of 1 minus arctangent of 0, which arctangent of 1 is pi over 4, minus arctangent of 0 is 0, and so this ends up just equaling pi over 4. So that is our first example done there. So the next example that we do, and again, this one right here was exactly lined up with the second equation, so we were able to do that. The next couple of things are going to require to use some u-substitution stuff. So for example 2, we want to do what's the integral of 1 over square root of 2 up to 1 of dx, all that over x, square root of 4x squared minus 1. So I'm going to try to pair that up with this equation here. So I'm going to bring this equation on down so we can kind of start looking at how do we algebraically manipulate this equation we have here to end up being like that format. So here's what we got to do. I'm going to start out looking at this inner part. Say if I have 1 over square root of 2 up to 1, and I have dx, all that over x, I need to evaluate this as a expression squared minus 1. So I think what squared, what when I put here, when I square it, would give me 4x squared? Well, 2x when I put there, 2 squared is 4, x squared is x squared. So at this point, we will let u equal the 2x. Then we say, okay, if u is 2x, then du would be 2dx. So I have the dx up here. I need the 2. And if I put the 2 up there, I'm going to need a 1/2 out front. So I can substitute in for the 2x, I can substitute in for u. And then 2dx, I can replace that with du. But the x over here, I need to solve this equation for x. I can move the 2 over as 1/2. So we get 1/2 u equals x. And now I have all the bits and pieces I need to plug into this. So I have 1/2. When I get some new limits of integration, I'll figure out in just a minute. 2dx becomes just du. X itself down there is going to become 1/2 u. And then we'll have square root of u squared, because 2x is u, so it'll be u squared minus 1. This 1/2 that's in the denominator, I'm going to push it out and make it out in the denominator of the front fraction of stuff we pushed out front. So I get 1 over 2 times a half, which y'all can note will cancel. Integral of du over u square root of u squared minus 1. And if I look at what I'm trying to integrate now, this right here is this expression here, but with u's instead of x's. So this will equal arcsecant of u. Oops, hang on. One thing I forgot to update my limits. So my limits of integration. To get my new limits, I'm going to say, all right, if I put 1 in for x here, if I put 1 in for x, I get a new limit, upper limit of 2. If I put 1 over square root of 2 in for x, I get 2 over square root of 2 for my lower limit. So when I do this, I get arcsecant of u evaluated from 2 over square root of 2 up to 2. This will be arcsecant of 2 minus arcsecant of, that would be 2 over square root of 2. And if we put this in the calculator, or you look on the unit circle, this will be pi over 3 minus that will be pi over 4. To help out with kind of seeing that one there, we should note if you have 2 over square root of 2, you can multiply the bottom and the top by square root of 2. This becomes 2 square root of 2 over 2, and the 2's can cancel, and that's really just square root of 2. So this 2 over square root of 2 here, that is just square root of 2. And that can help you get that from the unit circle. Then when we do this, let's see, we need an LCD, so this needs 4s, this needs 3s. So we get 4/12 minus 3/12 is a single 12, or pi over 12, sorry. And so we get our answer to that one. We had to algebraically shift some stuff around initially to allow us to use our u substitution. Okay, next one up, they want us to evaluate integral from 0 up to 3/4. They give us dx over the square root of 9 minus 16x squared. So we're going to say, okay, this looks a lot like, I think, the arcsine equation. If we look up here, arcsine equation has kind of that square root 1 minus x squared. And so we're going to try to get stuff lined up to pair up where we can match it with this equation here and use some u substitution with it. First thing I need to do is I need to algebraically pull out the 9 from the square root down there. So we get dx over square root of 9 times 1 minus be 16/9 x squared, like that. Square root of 9 is 3, so I can push that 3 out front. Since it came from the denominator, it's going to be out front as a 1/3. I have integral of 0 up to 3/4 dx over the square root of 1 minus, I need to rewrite this as some stuff squared. And then what's in here is what we'll use for u. So 16/9 is, if you square 4/3, you get 16/9, and if you square x, you get x squared. So we get this expression here. This is basically going to say that u is 4/3 x. Therefore, du will be 4/3 dx. So I need to put a 4/3 up here, which means I need to put a 3/4 out front. And we'll note the 3's can cancel here. And so I'm ready to do a u substitution now. I have 1/4. I'll need to find my new limits. If I put 0 in, 4/3 times 0 is 0. If I put 3/4 in, 4/3 times 3/4 is 1. So my new limits are 0 up to 1. 4/3 dx, that's du, so the top becomes du. And then I have square root of 1 minus 4/3 x is just u itself, so the 4/3 x becomes u. We get it squared like that. So we have this expression here. This is now ready to be arc sine of u. So this will be still 1/4 out front. This will be arc sine of u evaluated from 0 up to 1. Which will be 1/4 arc sine of 1 minus 1/4 arc sine of 0. So 1/4 arc sine of 1. Arc sine of 1 is pi over 4, so this is a pi over 2, because pi over 2 has y value 1, so this is a 1/4 times pi over 2. And arc sine of 0, you say what angle of sine has 0? Well, sine of 0 is 0, so this whole term here goes to 0. And we get 1/4 times pi over 2 is pi over 8 for our answer there. Okay, so next bit we're going to move on and take a look at a couple other, really just kind of one other expression that we need. So we get this equation, that's the integral of b to the x dx is equal to b to the x over natural log of b plus c. Get that expression like that. And what we want to do is there's two other expressions we want to go through and solve out here. So we get, for this example, get the integral from 3 up to 5 of 7 to the x dx. So if we try to evaluate this, this will equal, the antiderivative is this expression here, so it'll be 7 to the x over natural log of 7. And we'll be evaluating that from 3 up to 5, which will equal 7 to the 5th over natural log of 7 minus 7 to the 3rd over natural log of 7. And we can leave our answer like that if we want, or if you want to put it in the calculator, you get that's about equal to 8460.8. So either leave it like this, or you can put it in the calculator, get it down to there. This right here, for the AP test, use 3 decimal places. The book only used 1 for that expression. And the final one here from example 5, or final one here from this section. Example 5 wants us to do the integral from 0 up to pi over 2. They give us cosine of theta, and we have 10 to the sine of theta d theta. So I'm going to need to use u substitution. This is kind of pairing the b to the x equation on in with some trig stuff. So I'm going to let u be my sine of theta. Then du, derivative of sine is cosine, so we get cosine theta d theta, which I have the cosine theta d theta there. And so now whenever I go to integrate this, I'm going to need my new limits here in a minute. But what I'll get is 10 to the u, so it's 10 to the sine of x. Then cosine theta d theta becomes du. And for my new limit, sine of 0 is 0, sine of pi over 2 is 1. So when I go to take the antiderivative of this, I get 10 to the u. All that over should be natural log of 10. So we're using this equation here. We get b is 10, so it'll be 10 to the u over natural log of 10. That's evaluated from 0 to 1. So I get 10 to the first over natural log of 10 minus 10 to the 0 over natural log of 10. 10 to the 0 is 1, so this will be 10 to the first, which is 10 over natural log of 10 minus, this is really 1 over natural log of 10. So 10 over natural log of 10 minus 1 over natural log of 10 will give me 9 over natural log of 10. And that will be our answer. So we'll stop there on the section and say that's good enough.